Okay, so there's something interesting going on when we're dealing with metal carbonyl complexes, because you've done lots of chemistry on classic ligands like amine ligands and classic ligands like water ligands. And so amine ligands bind to transition metal centers of Lewis acidic transition metal centers like nickel-2 ions. So there's a lot of chemistry of nickel-2, a lot of chemistry of iron-3. These are the kind of ions that form complexes with simple donor ligands like an amine, like an ammonia ligand, like a water ligand. Okay? Now, what you have never seen, and what you will never see, is nickel-0 binding ammonia. Nickel-0 doesn't do it. There are no nickel-0 complexes of ammonia. You have to have a positive charge on the nickel. You have to make the nickel more Lewis acidic if you're going to bind your Lewis base of ammonia. So classic ligands like this do not make complexes with low oxidation state metals. It doesn't happen. So what is it about carbon monoxide that is special? Is it that carbon monoxide is this super base that is so basic it can bind to metal species that don't even know they're electron deficient? Okay? No. Carbon monoxide is not a spectacularly strong base. In fact, whereas you can imagine, and you have, protonated ammonia to make an ammonium cation, you can do that very readily, you need a very strong acid to protonate carbon monoxide to make the formyl cation. That species is not very stable at all. So it's certainly not the case that carbon monoxide is a spectacularly strong base. Far from it. So what is going on? Well, let's remind ourselves, maybe it's a little while since we've seen something like this. This is the molecular orbital diagram for carbon monoxide. So here are our molecular orbitals. And if we look at these molecular orbitals, what do we call the molecular orbital highest in energy that actually has a pair of electrons in it? It's the HOMO. Okay? So this is the highest occupied molecular orbital. It's the HOMO. And what is it? Well, if we look at our molecular orbital diagram, clearly it has a lot of carbon S character. What is it? Well, I think we know. It's the lone pair on the carbon. So for a synthetic chemist, this molecular orbital diagram, the highest occupied molecular orbital is this one, the HOMO, is essentially the lone pair on the carbon that we consider donating. So the HOMO is a lone pair on the carbon. Right, if this is the HOMO, we're probably on the right wavelength now. What do we call these two degenerate orbitals here? Yeah, they are the LUMOs. So we have the lowest unoccupied molecular orbitals, and they have Pi Star character. So on the next slide in front of you, we've actually drawn those. So we've drawn the lone pair on the carbon, and I've also drawn the Pi Star orbitals. Now, these Pi Star orbitals have some interesting properties.